Welcome to Chapter 1 of Advanced Spintronics, Magnonics and Spin Waves. In this chapter, we'll explore the fascinating physics of collective magnetic excitations. Spin waves are wave-like oscillations of magnetization that propagate through magnetic materials. When quantized, these excitations become magnons, the magnetic analog of phonons and photons. We'll learn how magnons enable novel information processing paradigms with potential for low-power computing. Spin waves are collective excitations of magnetic moments in ordered magnetic materials. In a ferromagnet, neighboring spins are coupled by the exchange interaction described by the Heisenberg-Hamiltonian. When one spin precesses, it drags neighboring spins with it, creating a propagating wave. This is analogous to water waves or phonons in a crystal lattice. The wave carries angular momentum and energy through the material without moving charge. The dispersion relation describes how spin wave frequency depends on wave vector. At short wavelengths, exchange interactions dominate, giving a quadratic dispersion. Omega equals gamma times h plus dk squared. At long wavelengths, dipolar interactions become important, creating more complex behavior. The crossover happens where the exchange contribution dk squared becomes comparable to the dipolar field, which for yttrium iron garnet corresponds to wavelengths of roughly 100 nanometers. This dispersion determines spin wave propagation characteristics. The Daman-Eshbach mode is a special magnetostatic surface spin wave that propagates along the surface of a thin magnetic film. These waves have amplitude that decays exponentially into the bulk. Remarkably, they exhibit non-reciprocal propagation. They travel more easily in one direction than the other. This asymmetry arises from the interplay of magnetization direction and wave vector, and can be exploited for isolators and circulators. Just as photons are quanta of light and phonons are quanta of lattice vibrations, magnons are the quantized excitations of spin waves. Each magnon carries energy h-bar omega and angular momentum h-bar. The Hallstein-Primakov transformation provides the mathematical framework, expressing spin operators in terms of bosonic creation and annihilation operators. This allows us to treat the magnetic system quantum mechanically. Magnons are bosons and follow Bose-Einstein statistics. The average occupation number follows the familiar Bose-Einstein distribution formula. At finite temperature, thermal magnons reduce the total magnetization, leading to Bloch's famous T to the 3/2 law. This describes how magnetization falls away from its zero temperature value at low temperatures. It is an expansion valid well below the Curie temperature. Close to the Curie point, the magnetization instead follows critical behavior and vanishes with a different exponent. Magnonic crystals are the magnetic analogs of photonic crystals. By creating periodic structures with modulated magnetic properties, we can engineer the spin wave dispersion. This creates band gaps, frequency ranges where spin wave propagation is forbidden. The gap appears at wave vectors satisfying the Bragg condition. These structures enable filtering, waveguiding, and other signal processing functions for spin waves. In 2 dimensions, magnonic crystals offer even richer physics. Antidot lattices, where periodic holes are etched into a magnetic film, create scattering centers for spin waves. Alternatively, arrays of magnetic nanodots exhibit discrete mode spectra due to confinement. 2-dimensional structures can achieve omnidirectional band gaps, blocking spin waves regardless of propagation direction. Common geometries include square, hexagonal, and honeycomb lattices. The spin wave Mach-Zehnder interferometer is a fundamental building block for spin wave logic. An input spin wave splits into 2 paths, each accumulating different phases. When recombined, interference determines the output. If the phases match, constructive interference gives output 1. If they differ by pi, destructive interference gives output 0. By controlling the phase in each arm, we can implement various logic gates including XOR. The majority gate takes 3 inputs and outputs the majority value. Using spin waves, This is implemented by combining three waveguides at a single junction. When two or more inputs are in phase, constructive interference produces a strong output signal representing logical 1. The beauty of this approach is that complex logic functions emerge naturally from wave physics, with low power consumption and inherent parallelism. Practical magnonics requires understanding propagation characteristics. The group velocity determines how fast spin wave packets travel, given by the derivative of omega with respect to k. Various damping mechanisms limit propagation distance. Intrinsic sources include Gilbert damping from spin-orbit coupling and magnon-magnon scattering. Extrinsic sources include 2-magnon scattering from defects. The propagation length depends on velocity divided by damping rate. Numerical simulation reveals spin wave dynamics in detail. Using finite difference time domain methods, we can solve the Landau-Lifshitz-Gilbert equation on a grid. The results show spin wave packets propagating from a localized source, with amplitude decaying due to damping. Spacetime plots reveal the dispersion. Different frequency components travel at different speeds, causing wave packet spreading. These simulations guide device design. At high amplitudes, nonlinear effects become important. Parametric amplification uses a microwave pump at twice the signal frequency to amplify spin waves. This is a three-wave process conserving both energy and momentum. Above a threshold pump power, the signal grows exponentially. This technique can compensate for propagation losses and is essential for long-distance spin wave transmission and signal processing. When nonlinearity balances dispersion, localized wave packets called solitons can form. These maintain their shape during propagation, described by the nonlinear Schrödinger equation. Spin wave solitons have been observed experimentally. Even more remarkably, two solitons can pass through each other unchanged, exhibiting elastic collision behavior. Solitons could enable robust information transfer in magnonic circuits. Under strong pumping, magnons can accumulate in the lowest energy state, forming a Bose-Einstein condensate. This has been achieved in YIG at room temperature using parametric pumping. The condensate exhibits spontaneous coherence and long-range order. Because it is continuously pumped rather than in true thermal equilibrium, researchers describe it as superfluid-like, and the extent of that analogy is still an active question. Magnon BEC opens exciting possibilities for coherent magnonics and novel collective phenomena. Magnonics offers diverse applications across computing and communications. Spin wave logic gates could enable ultra-low power processing. Magnonic filters exploit band gaps for signal processing. Magnon-photon coupling enables microwave-to-optical conversion. Neuromorphic computing benefits from nonlinear oscillator dynamics. Looking forward, quantum information applications may leverage single magnon manipulation and entanglement. Let's summarize the key equations from this chapter. The exchange-dominated dispersion relation shows frequency increasing with wave vector squared. Magnon occupation follows the Bose-Einstein distribution. The Hallstein-Primakov transformation connects spin operators to bosonic operators. Group velocity is the slope of the dispersion curve. Propagation length scales inversely with damping. These equations form the foundation for magnonic device design. We've covered the fundamentals of magnonics: spin waves as collective excitations, magnons as their quantum particles, magnonic crystals for band engineering, and spin wave logic for computation. We explored nonlinear effects including parametric amplification, solitons, and Bose-Einstein condensation. These concepts enable a new paradigm for information processing. Next, in Chapter 2, we'll explore quantum spintronics and spin qubits.